very much.
No worries.
Okay, well, yeah, so thanks, Paola and Athena, for organising the workshop and inviting me. Very happy to be here. So it's really interesting to hear the history of what Kevin did, because it's basically the same thing for me. So teaching, well, I mean, the reason I got into Lean, because I've been teaching its first year module on introduction to proof for some time. I noticed that proof was a big problem for many students, and I came across Jeremy Avogad's. I was thinking about type theory for a long time before I started working on Lean, and I came across Jeremy Avogad's Logic and Proof website. I thought, oh wow, this is brilliant, and it taught me a lot about logic. I think in the same way that Kevin was talking about what's meant by if X is a real and blah, blah, blah. Yeah, so none of these things I really understood before. And I'm going to talk about lean games in this talk, and part of this is because of the issues that Kevin has about getting students to use this formal language, lean. What are the ways around it? I'll talk about games for teaching maths and games for teaching formal maths and lean games. Okay, so I'm not an education specialist, but I've just done a bit of reading in advance of the talk today. So so there's this French education theorist, Guy Brusseau. He did a bunch of stuff in the 70s, and one of the things he did in 98 was this theory of didactical situations in mathematics. So what's a didactical situation? A didactical situation is a situation designed by a teacher to provoke some learning in the student. That's what's meant by a didactical situation. And here's an example of a didactical situation. Well, here's an example of a game. So the game is raced to 20. So there's a tally that starts off at 0, and you've got 2 players, and each player takes turns adding 1 or 2 to the tally, and you win if you get to 20. That's it. So what? I don't know. We probably don't have time to play the game. So you imagine that you'll play the game. What should we play the game for? 30 seconds. Well, I don't know. Turn to the person next to you. I solved it. You already solved it. Yeah, you're not high school students. This is the problem. Okay, you will solve the game then. Imagine you're not a professional.
Yeah. I played this game with my kids though.
Oh, okay. Yeah. Okay. Well. Okay. Let's imagine. Let's imagine there's some let's imagine we've done the So the game itself is not a didactical situation. What makes it a didactical situation is the teacher doing something. So the teacher explains the rules of the game to start with. In Brusseau's work, he says, and then the teacher brings the student in, plays the game with one student. Then another student comes in, takes over from that student, and then the whole class splits up into pairs. They play the game. And since they're high school students, they maybe don't realise immediately what the strategy is, but they play the game, and maybe by playing the game a few times, they come up with some idea of how to win. Not necessarily, they don't necessarily have a theorem. This is the strategy, and here's the proof. But so this is what Brusseau realised, is that actually the strategy comes before the proof. You understand what to do before you know why. Well, let's see how this works. I think it's working fine, thanks. So so you've got the one-to-one thing, and then you get groups working together, and then they try to explain to each other, well, why is it? What is the strategy? Can I formulate a proposition? Why, what is the rule? So okay, so what you might, so if you play this game, there is a strategy. So what you want to ensure is that your opponent is always left with a number that's divisible by 3. So I suppose the lesson that's being taught here, or the mathematical concept that this game is meant to teach, is something about, I don't know, either divisibility or maybe induction, possibly, I don't know. So it's about congruences. Yeah, there are many things in which you could teach using this game. So Brusseau uses this word re-decontextualization. So what's up with that? So the idea, he's saying, is that when people do research in mathematics, there's some context in which they do the mathematics, but when they write up their research papers, they decontextualize the history of how you came up with the result. disappears in the research paper. What has to happen in the didactic situation is after the didactic situation, okay. So you've got the research that's been decontextualized, and then you need to re-decontextualize. Wait, no, sorry, start again. So it's now contextualized for the student when you're doing the didactics game, and then the student then needs to re-decontextualize when they form the knowledge. They need to then do what the researcher does to actually do this decontextualizing. Right, so I hope I've understood that. I'm not a specialist, so people will correct me afterwards. Okay, so what about, so that's a game, but it's not about proof so much. So what about formal languages? Are there games with formal languages? So I discovered that there's actually this really old board game, a dice game, called Woof and Proof. So it was by this professor at Yale, I think he was a law professor in 1961. It's a dice game. So the dice, on the dice, you've got different dice. You've got some dice that represent symbolic propositions and some that represent rules of inference. And you roll a dice and you construct a goal. So you're meant to prove this, and you've got some resources, and these resources can form your premises. And then at each stage of the game, the players take turns either trying to use a rule of inference or to challenge to say, no, actually, you can't prove the goal from these premises. And the thing is, this is much more challenging than the rule race to 20, because with the race to 20, it's easy to say what the rule is. The rules of the game are easy to explain. With formal proof in propositional calculus, the rules are much more complicated. And this is one of the issues of teaching mathematics. And everything's been shared over here, right?
Yeah,
Okay.
should be.
Yeah. Yeah, and I'm sure this is the problem that everyone who's trying to teach undergraduate mathematics does encounter. It's not as simple as the race to 20. So this was the 1960s. What's happened since then? Well, since then we've got computers. I guess they had computers in the 1960s, but they weren't so readily available. So one thing we've got here is, has anyone come across Scratch? Yeah, so Scratch here is a visual programming language. So you can write little programs by just dragging and dropping blocks. So here's a simple program that computes the greatest common divisor of two numbers, and it's okay. So Scratch is a what's the word? Procedural programming language? Boo! The worst kind. But there we are. I guess that's what we have to do. So I'm going to see if I can. I've got some Scratch here. Yeah. So I'll just show you how it works. So this is the thing I wrote. So yeah, so just to indicate how one writes a program, you just drag and drop stuff. Maybe I'll just create something. Oh, cool. I'm not signed in here, so I can't create things. Yeah. Yeah. So anyway, this is what it looks like, and you've got these little blocks that you drag. So you drag and drop, and if we go back to, I used to have this. There we are. So this here, for example, this shape here is a logical operator. Right? So the b equals 0. What's nice about these visual programming languages, I'm just going to go back to my slides, is that they overcome some of the difficulties of. Oh, it's not working. Oh yeah, they overcome some of the difficulties of things like woof and proof, or just learning programming without having the blocks. Why? Well, there are two things. First of all, you've got all of the blocks ready to go, so you know what rules you can use. They're presented to you. But there's something more important than that: syntax errors. So what kind of syntax error can you make when you're doing programming with Scratch? Well, basically, the block isn't going to fit into the thing of the right shape. And that's quite obvious if you've made a syntax error in Scratch, because your block won't fit in there. So that's one of the big benefits of something like Scratch. Okay, but we're not talking about computer programming. We're talking about logic. So here's another great game. It's called The Incredible Proof Machine. So this is by Joachim Breitner of Karlsruhe, I think. So with this game, there are blocks again, but these blocks, instead of being programming blocks, they're little logic blocks. So here, for example, is a block that does conjunction elimination. So you've got a conjunction of two things that splits it up into its left and right parts. So what you're presented with this game is you're presented with a premise or several premises, and you've got some conclusions, and then you're meant to fill in what goes in here. So like Scratch, you've got the blocks, and you've got the feedback as to whether or not it's working. It's a little different. You don't have the kind of diamond shapes where it's obvious that the syntax is incorrect, but it's still clearer when you've made a mistake. So the question I got is, to what extent does this translate into writing handwritten proofs? This is a two-dimensional proof. Usual maths proofs are one-dimensional. Okay, so finally, I'm going to talk about lean games. So the Lean Game Maker engine was developed by Mohammed Hedram Imperial College, 2019, and the first and most popular application was Kevin's natural number game. But I'm going to talk about a different game. So this game is called the MIU game. So the MIU idea was developed by Douglas Hofstadter in his 1979 book Gödel, Escher, Bach. So it's a little formal language, basically. So here's the formal language. You've got three letters in your formal language, M, I, and U, and you've got an axiom, which is MI, if you will, and then you've got these four rules of inference, or production, from which you can create new words in your language. So if you've got an XI, where X represents any derivable string, then you can produce XIU, etc., etc. So Hofstadter's question is, can you produce MU? Can you produce the string MU? The answer, as it transpires, is no. And the question is, why can you not produce MU? And there's arithmetic in this. There's actually something to do with, again, congruences modulo 3. So it's a bit like going back to the race to 20 thing that Rousseau was talking about. Only it's a much more sophisticated game, so maybe not something that a small child can understand. Though I did do this game with students at the Exeter Mathematics School, but it's something certainly that students can understand. Now let's, in the next few minutes, we'll actually have a look at this game. So let's see. I will go over to. Now is that? No, that's not displaying, is it? So I'll need to. Yeah.
Still on presentation.
I'm still on presentation mode.
So now I should be able to see the one you wanted. Which one do you wanted?
Yeah, we'll go to the Chrome and we'll go to the MIU game. Lovely. Okay. Fabulous. Okay, so let's just go here. So this is what, if you make something with Mohammed's Lean Game Maker, this is the kind of game that's produced. So what you see here on the right is the worlds of your game. So I've got several worlds: rule, practice, game, existence, numbers, etc., etc. And all of the text. So I'll just click on here. So how do you produce, if you're thinking of making your own game, how do you produce a game file? Well, the game file is simply an ordinary lean file, and the text is produced in Markdown, Showdown, something like that. So it's actually really easy to make one of these games. Going back to Rousseau and his didactical situations, the first time I encountered a lean game, I guess it was the natural number game, it wasn't immediately evident to me what I was meant to do. So it's not evident that you're actually meant to click in here and do something, I had to read what was going on. This is why you need.
Apologies for my crappy.
No, the point I'm making is that when we're teaching students, I think it needs to be done in situ. Yeah. So this is something I have been doing a little bit at Exeter, and I'm going to take it forwards in the future because, like Kevin, I've realised you can't just say, "Here's this wonderful system, go away and work on it." It's not going to happen. You actually need to maybe do it in the lecture and show the student how it works and get them to work on it. Okay, so here we've got the task to prove that MI is derivable in this language. And you can read all of the text. It actually tells you somewhere in here. This is crappy as well. So like hidden in this verbiage is what you're meant to do. It actually says what you're meant to do. You're meant to type in from the MI in place of sorry, which I've just deleted. So if I type in from the MI, from the underscore MI, and then it says no goals here. So yeah. So what happened before is that it's actually telling you what you're meant to prove. So if you're not familiar with Lean, that's the way it works. You've got the goal, the thing you're meant to prove, and you type some stuff, and then hopefully it proves what you're trying to prove. Now, like the Scratch game and the other games we discussed, the nice thing about Mohammed's engine is that you can have these little things on the side that are telling you what the tactics are. So the tactics are, in some sense, I don't know, well, they're meta programs within Lean. So you've got the from tactic. It says from is a finishing move used to close a goal, and you've got theorem statements, which in this case constitute the rules of the language at the moment. So the rules of the language are that MI is derivable. Is that visible? Can you see that? And then we've got the full rules of the MIU system, and you can go through as you go through. I'm not going to spend too much time on this. You can go through the levels. You get to learn more and more terms of the language. So one of them is apply, for example. So let's just get rid of this. So we want to prove MII can be derived in this language. So there are several ways of doing it. We can either do it using a forward proof or a backwards proof. So let's look again at the rules of the language. Okay, so we know that MI can be derived. That's our axiom. We know if XI can be derived, so can XIU. We know that if MX can be derived, then so can MXX. So the student thinks, well, which of these rules is going to help me to prove this statement? Clearly, the second rule is helpful. Because we know MI can be derived, and therefore we can derive MII. But we can use that backwards. And this is one nice thing about Lean, actually, is that, and one difference in the way in which maths is often presented at the undergraduate level, is that maths is often presented forwards. We present our proofs forwards, which is already that decontextualizing thing that happens. Which isn't usually how proofs are actually developed. We don't start with some premises and go forwards and finally we get a conclusion. There's usually actually a bit of backwards and forwards. We've got the goal. We can, well, how do I prove this goal? I might, if I can prove something else, then I can prove the goal. So that would be a backwards proof. So I know that if I can prove MI, then I can prove, or if I could derive MI, then I could prove or if I could derive MII. So we can say apply rule 2. And we need to say what we're applying it to, so I guess I. And now let's change the goal to one of proving that MI can be derived. And we can then do from MI. And we've proved that. Okay. So we derived MI. So this was a simple, this is our simple rule practice world in which you get to work with very simple Lean tactics. And then for the rest of this world, we go through more and more sophisticated things involving, induction on lists. And then eventually, hopefully, you can prove by the end of it that this MU is not derivable in the MIU system, but that requires understanding various things on logic and induction and so forth. But that's just wanted to show you an example of how to use Lean games. Thanks.
Thank you. Thank you. I would like to suggest that we take 5-10 minutes for questions to Gihan and Kevin. And I have a question for Kevin online. So Claudia asks whether you think that when you did the project with the first years, when you taught in the first year, whether you thought that using Lean impact